Welcome back to the Deep Dive. We're here to take your complex sources, put them through our knowledge extractor, and really give you those fundamental insights, the aha moments that actually matter. Today we're tackling a concept that, honestly, sounds ripped straight from the best kind of science fiction, but it's being taken seriously by climate scientists, astrophysicists. It's fascinating. We're asking you to grapple with, well, the sheer immensity of geological time. To start with this thought experiment. Imagine some advanced species, maybe hundreds of millions of years from now, digging around on Earth. What definitive, really long-lasting proof would they find that we were here? Now, flip that perspective around. If our species just vanished tomorrow, and say 50 million years went by, what proof would a future civilization find that we ever existed? And here's the kicker. What if we weren't the first? What if, millions and millions of years before the first primates were even a thing, there was another advanced, maybe even industrial civilization right here on Earth?
That right there is the heart of this deep dive, the Silurian Hypothesis. It's this really elegant thought experiment. It was formally proposed by astrophysicist Adam Frank and climate scientist Gavin Schmidt in a paper back in 2018. And it's really important to understand what they were trying to do. They weren't actually trying to prove that, dinosaurs built skyscrapers or anything like that. In fact, they explicitly say they strongly doubt any kind of pre-human civilization existed.
Right, they're skeptical themselves.
Exactly. Their real goal was sort of twofold. First, they wanted to figure out what the definitive geological fingerprint of an industrial society actually is. And second, use that definition to help with two really big scientific endeavors.
Oh, okay, so it's like a tool. If we can figure out what a, say, 50 million-year-old technological footprint looks like, then we're also defining how long our own impact, the Anthropocene, the age of humans, might last geologically.
Precisely. And it also radically improves how we might search for alien life, astrobiology. If we know what kind of subtle geological traces to look for here, maybe we can look for similar things on other planets.
That makes sense. Sort of refining the search parameters.
Exactly. And just quickly, to clear up any confusion about the name, in a fun little nod to pop culture.
Right, the Doctor Who connection.
Yes. It comes from the reptilian humanoids in the BBC series Doctor Who, the Silurians. They supposedly had this advanced civilization way before humans. It's not named after the actual geological Silurian period. That was much, much earlier, like 440 million years ago.
Okay, good clarification.
Yeah.
So let's dig into this. Frank and Schmidt basically invented, the opposite of SETI, the search for extraterrestrial intelligence. Instead of telescopes looking out,
we're using geology to look down into Earth's own deep past for these sort of ancient ghost traces.
But if even the authors are skeptical, and common sense says finding, a dinosaur cell phone is ridiculous, why is this search so incredibly difficult? What makes finding evidence so hard?
The difficulty, well, it really boils down almost entirely to the immense, almost unimaginable scope of geological time. And to really get a handle on the challenge, we need to sort of establish the timeline first. The authors kind of benchmark this by looking at when there was enough available energy, enough fuel to power an industrial society like ours. They point out that there's been sufficient fossil carbon, coal, oil available since roughly the Carboniferous period.
And that was
around 350 million years ago.
Million years. Okay, let's just pause on that number. Modern humans, Homo sapiens, we've only been around for maybe 300,000 years, right?
About that, yes.
So if you imagine that entire 350 million years as just one single calendar year, our entire human history is what, like the last 10 minutes of New Year's Eve?
Something like that, yeah. And our industrial era, the time we've been having this massive global impact, that's less than the final second before midnight. We are, geologically speaking, just a flash in the pan.
A cosmic blink. Okay, so any civilization that might have existed in that enormous stretch of time between the Carboniferous and us, they're up against this relentless geological erasure. You called it a geological buzzsaw.
That's a good way to put it. And this leads us straight to what we can call the fossilization problem. People immediately think, oh, maybe we'll find a pre-human artifact, a tool, a piece of a building. But in this context, that's almost pure fantasy.
Why? Stuff gets fossilized all the time, doesn't it? Dinosaur bones, shells.
Yes, but fossilization mainly happens to organic material, bones, teeth, wood, shells. And even then, it only happens under very specific, pretty rare conditions, like rapid burial in sediment, low oxygen to prevent decay. You need the right chemistry.
Yep.
Steel, concrete, ceramics, plastics, the stuff we build with. They generally don't mineralize in the same way. They tend to oxidize, rust, crumble, dissolve chemically over geological timescales. They just don't play by the same fossilization rules.
But what if they had, super advanced materials, maybe something incredibly durable we haven't even invented?
Even then, even if you had some miracle material, the Earth itself is the ultimate eraser. And that's where erosion and plate tectonics come in.
Right. The planet is constantly changing its surface.
Constantly. We have wind, water, ice, all relentlessly grinding down surface structures into tiny sediments, sand, silt, clay. Then those sediments get buried under more sediments, compressed, heated.
And sometimes they get pulled down deep into the Earth.
Exactly. That's subduction. It's where one tectonic plate slides underneath another, carrying surface rocks deep down into the Earth's mantle. Once that material gets down there, it's subjected to incredible heat and pressure. It melts, it gets mixed up, chemically altered, what we call metamorphic alteration.
So it's basically reset. Any structure, any complex chemical signature from a civilization is just gone, wiped clean.
Wiped clean. That material might eventually come back to the surface, maybe millions of years later, as volcanic rock or something similar, but it's completely reformed. The original information is lost.
So anything built on the surface probably gets ground down, and anything buried deep gets melted. Is that why the sources stress that most of the exposed rock we see on Earth's surface today is relatively young, from the Quaternary period?
That's a huge part of it, yes. The Quaternary only started about 2.5 million years ago. Most of the stuff older than that is either buried really, really deep under kilometers of younger rock and sediment, or it's already been through that tectonic recycling process.
2.5 million years. That's still a long time, but compared to 350 million.
It's nothing. So finding a physical artifact from, say, 50 million years ago means finding rock strata from that specific time that has somehow avoided being deeply buried, intensely heated, squeezed, or chemically altered for all those millions of years. And it has to be accessible near the surface today.
It sounds like looking for a single specific grain of sand on, all the beaches in the world, but knowing that 99.9% of the beaches have already been melted and turned into new rock.
That's a pretty good analogy, actually. The odds of finding direct physical evidence are just vanishingly small. So the real value of the Silurian hypothesis isn't really about finding a fossilized spaceship.
It's about forcing us to think differently.
Exactly. It forces scientists to pivot. If we can't find the tools, we have to look for the impact. We have to figure out what the large-scale, persistent geological signature of a technological society looks like over these immense timescales.
Okay, so stop thinking about finding a specific object and start thinking about, the planet's metabolism going haywire because of a civilization's activity.
That's the direction, looking for the indirect fingerprints.
Right, so if direct artifacts are pretty much off the table, the whole search hinges on finding these indirect clues, these sort of global, persistent chemical signals or sedimentary layers. The smoking guns buried in the rock record. We're basically looking for the planet-scale waste products of a civilization. And the most obvious, the biggest impact a technological society has is probably on its climate and atmosphere, right?
So are we looking for signs of super rapid climate change, like way back then?
That's definitely one of the primary targets, yes. The sources suggest looking for evidence of massive, very rapid, but maybe geologically short-lived spikes in global temperature and big disruptions in the carbon cycle, all embedded in the rock strata.
Okay, but the Earth's climate has changed dramatically throughout its history, naturally, hasn't it? Ice ages, warm periods. How do you tell the difference between a natural climate shift and one caused by, dinosaur factories?
That is the absolutely critical challenge. How do you distinguish a technological shock from a purely natural event? The authors use a specific example as a comparison point, the Paleocene-Eocene thermal maximum, or PTM. The PTM, that was around 55 million years ago. I remember reading about that, a big natural global warming event.
Exactly. About 55 million years ago, global temperature shot up dramatically. It was associated with huge releases of carbon into the atmosphere and oceans. So on the surface, it looks like the kind of signal we might be searching for.
So if we find a similar spike from, say, 100 million years ago, how do we know if it was another PTM-like natural event or something else? What's the telltale sign of technology?
It really comes down to two main things: the rate of change and the specific isotopic signature of the carbon that was released.
The speed.
Yes, the speed. The PTM, while rapid in geological terms, likely unfolded over thousands, maybe tens of thousands of years. Human industrial civilization, on the other hand, has pumped a comparable amount of carbon into the atmosphere in just a couple of centuries.
Ah, okay, so centuries versus millennia. That's a huge difference in pace.
A massive difference. And that difference in rate should leave a distinct signature in the sedimentary layers. If future geologists drilled a core sample, they could analyze the layers very finely. A natural event like the PTM might show the carbon isotope shift spread out over, say, several centimeters or even meters of sediment representing thousands of years.
Whereas a technological release
Would be incredibly abrupt. It might appear as an almost instantaneous spike, compressed into a millimeter-thin layer or maybe even less. That extreme sharpness, that concentration in time, would strongly suggest a very fast, non-natural trigger.
like flipping a switch, geologically speaking. Okay, rate is one thing. What about other chemical clues in the sediments? You mentioned anomalies.
Right. Industrial activity doesn't just release carbon dioxide. It potentially leaves behind all sorts of other weird chemical traces, things that just don't occur naturally in those combinations or concentrations, buried deep underground or on the ocean floor.
Like what specifically? What kind of unnatural chemistry are we talking about?
Well, think about large-scale agriculture. Any big civilization needs to feed itself, and that often means manipulating the environment. The sources mention looking for evidence related to artificial fertilizers.
How would fertilizer leave a trace millions of years later?
It's about disrupting natural cycles, particularly the nitrogen cycle. Making artificial fertilizer, like ammonia using the Haber-Bosch process, requires pulling nitrogen gas out of the atmosphere and fixing it industrially. This process can alter the natural ratio of nitrogen isotopes N14 and N15.
Isotopes again. So you'd look for a layer of sediment where the nitrogen isotope ratio is suddenly wrong, skewed compared to the layers above and below.
Exactly. If you find a distinct layer with an unnatural N15 abundance, that points towards massive industrial-scale manipulation of the nitrogen cycle, most likely for agriculture. It's a subtle but potentially very powerful fingerprint connecting food production to geology.
That's pretty cool, connecting farming to rock layers. What about energy, besides fossil fuels?
If a civilization was really advanced, they might have tapped into other energy sources. The sources speculate about things like large-scale geothermal energy. Imagine drilling deep and extracting heat from the Earth's crust on a massive scale.
How will that leave a trace?
It could potentially alter the chemistry of deep underground water reservoirs, or even leave subtle traces in igneous rocks formed later. You might look for unusual concentrations or ratios of elements associated with deep geothermal fluids, things like silicon, maybe specific trace metals, or sulfur isotopes suggesting a large-scale artificial hydrothermal system was active.
So evidence of messing with the Earth's internal plumbing on a planetary scale. Okay, now let's talk about waste. Things built to last, or at least things that refuse to disappear. Plastics are the obvious modern example. How long could they possibly last?
The persistence of waste is a really key indicator. While natural organic materials decay and even metals corrode, many materials engineered by industrial societies are designed not to break down easily. Plastics are a prime case.
But they do break down eventually, don't they, into microplastic?
They break down, but they don't necessarily break apart chemically, not fully. They become smaller and smaller particles, microplastics, nanoplastics, but the synthetic polymers themselves are incredibly persistent. They get incorporated into sediments, soil, even rock.
So what would future geologists actually find?
Geologists are already talking about technofossils. The sources suggest that future researchers might find a distinct sedimentary layer containing a high concentration of these microscopic plastic fragments. Perhaps they'd even find fused conglomerates of melted plastic mixed with sand and rock, something people have started calling plastiglomerate.
Plastiglomerate.
Right.
A rock made partly of plastic.
Essentially, yes. Finding a widespread layer like that, full of complex synthetic polymers that simply don't exist in nature, would be an absolutely unmistakable marker of an industrial civilization that produced plastics on a massive scale. A plastic horizon in the rock record.
Wow. Okay, so we have climate spikes, weird nitrogen ratios, maybe geothermal signatures, plastic horizons. These are getting pretty specific. But even plastics might chemically degrade or get buried too deep over, say, hundreds of millions of years. This brings us to the really durable stuff, right? The potentially ultimate signature.
Yes. This is where we move from looking at the environmental consequences of technology, to looking for the direct chemical fingerprint of the technology itself, specifically nuclear technology. We're talking about isotopes again, but ones that nature simply doesn't create under normal Earth conditions.
Right. This seems like the most powerful evidence. Not just circumstantial stuff like climate change or plastics, which might have weird natural explanations, but actual atomic signatures that could only be made by advanced technology. So, what are these definitive isotopes?
The most compelling evidence, the sort of holy grail, would be finding highly specific isotopes, particularly heavy ones, that have no significant natural source on Earth today. Nature makes elements and isotopes in stars, supernovae, and through radioactive decay chains over billions of years. Industrial civilizations can make unique ones much faster, using things like nuclear reactors or particle accelerators.
Okay, so what's the specific element? What's the golden ticket isotope that, if found in an ancient rock layer, basically proves a technologically advanced civilization was there?
The ultimate hypothetical find, according to Frank and Schmidt, is plutonium-244.
Plutonium-244. Why that specific one?
There are a couple of really critical reasons. First, its half-life. Pu-244 has a half-life of about 80 million years. Now, that's relatively short compared to the age of the Earth, but it's long enough.
Long enough that if a civilization existed, say, 50 or 60 million years ago and produced it,
there's a chance some of it, or at least its distinct decay products, could still be detectable today. It hasn't completely vanished from the record yet, potentially.
Okay, so the timing works out. What's the second, maybe more important reason?
The second reason is the clincher. There is essentially no naturally occurring plutonium-244 left on Earth. Any Pu-244 that was created when the solar system formed billions of years ago has long since decayed away because of that 80 million year half-life. The only way Pu-244 arrives naturally now is in absolutely minuscule trace amounts from things like supernova explosions reaching Earth.
So finding any significant concentration of Pu-244 in a specific geological layer from, say, the Eocene epoch
could basically only mean one thing. A technologically advanced civilization was present and was actively creating transuranic elements through nuclear processes. It's about as close to a smoking gun as you can get in geology.
But wait, if the half-life is 80 million years and we're looking back 50 or 100 million years, wouldn't most of the original Pu-244 be gone anyway? How would we even detect it?
That's a fair point. We might not find detectable amounts of the original Pu-244 isotope itself, especially if the civilization wasn't around for very long or didn't produce vast quantities. This is where the really clever part of isotope analysis comes in, looking for the decay products.
The daughter nucleus,
Yeah.
what it turns into as it decays.
Exactly. Pu-244 decays primarily through alpha decay, kicking off a long-chain reaction that eventually leads to stable isotopes, particularly of elements like uranium and thorium. The key is that this decay path produces a very specific, unnatural ratio of these daughter isotopes in a localized area.
So you wouldn't necessarily look for the plutonium itself, but for a weird localized pocket of, say, unusual thorium isotopes that shouldn't exist in that specific combination naturally.
Precisely. If you find sediments highly enriched in these specific decay products with isotopic ratios that don't match any known natural process, that serves as extremely strong evidence that an artificial parent element like Pu-244 used to be there. It's like finding the specific type of ash left by a unique kind of fire, even long after the fire is out.
That's incredibly clever. Forensic geochemistry. We actually know this kind of analysis works over truly immense timescales because of that amazing natural phenomenon in Africa, right?
Yeah.
The Oklo reactors.
Oh yes, the Oklo analogy. It's fundamental to the Silurian hypothesis because it proves that these kinds of isotopic signatures, even from nuclear processes, can be preserved and deciphered billions of years later.
Okay, let's quickly recap Oklo and Gabon because it's just such a wild story. What exactly happened there, like 2 billion years ago?
Right, around 2 billion years BP, before present conditions at Oklo were just right for natural nuclear fission to occur. Back then, the natural concentration of the fissile isotope uranium-235, U-235, was much higher than it is today, maybe around 3%.
Which is similar to the enrichment level needed in many modern nuclear reactors.
Exactly. And critically, groundwater seeped into these rich uranium deposits. The water acted as a neutron moderator, slowing down neutrons released by natural uranium decay. When the concentration of U-235 and the water conditions were right, it reached critical mass, and spontaneous, self-sustaining nuclear fission chain reactions started.
Nature built its own nuclear reactors.
Several of them, it
Yeah.
seems. And they apparently operated intermittently for hundreds of thousands of years. They'd run until the heat boiled away the groundwater moderator, then shut down, cool off, let water seep back in, and start up again. A natural pulsing reactor.
Mind-blowing. But the key question is, how did scientists figure this out 2 billion years later? All the really exotic, short-lived fission products would have been long gone by then.
They used isotopic analysis, focusing on two main things. First, they looked at the fuel itself. In the Oklo ore samples, they found that the concentration of uranium-235 was significantly depleted. It was lower than the standard natural abundance found everywhere else on Earth.
Because it had been burned up as fuel in the natural reactors.
Precisely. That was the first big clue. But the definitive proof came from analyzing the fission products, the isotopic remnants, the nuclear ash. They looked at elements like neodymium and ruthenium.
Okay.
These elements have several stable isotopes. When they're formed naturally through geological processes or stellar nucleosynthesis, they occur in very specific, predictable ratios. However, when they are produced as byproducts of nuclear fission, the ratios of their isotopes are completely different, skewed in a very characteristic way that only fission can produce.
So the scientists found neodymium at Oklo that had an isotopic fingerprint-matching fission, not nature.
Exactly that. They found isotope ratios for neodymium, ruthenium, and other elements that could only have been created through sustained nuclear fission reactions. That isotopic signature was preserved for 2 billion years.
Wow. So Oklo provides undeniable proof.
Yeah.
If nature's relatively gentle fission process leaves a clear, readable signature for 2 billion years, then the potentially much more intense, widespread, and chemically unique processes of an advanced industrial civilization
Should absolutely leave a detectable chemical or isotopic signature across mere tens or hundreds of millions of years. The physical structures might vanish, but the chemical ghosts, especially the isotopic ones, are likely much more resilient.
The rocks remember, even if it's just at the atomic level.
So you take this realization that finding direct physical evidence on Earth is incredibly hard, maybe impossible, but that these subtle chemical and isotopic traces might persist, and it naturally leads Frankenschmidt to think about, well, looking elsewhere.
Right. This brings the astrobiology connection back in. If we're struggling to find traces of a hypothetical ancient civilization here, partly because Earth is so active geologically, maybe the evidence isn't on Earth anymore.
Or at least maybe better evidence is off Earth. The sources specifically speculate that finding proof might actually be easier on other celestial bodies like the Moon or Mars.
Why would the Moon or Mars be better places to look for traces of an ancient Earth civilization than Earth itself? That seems counterintuitive.
It comes down to preservation. Earth is incredibly dynamic geologically. We've talked about the constant erosion, the plate tectonics, the subduction, the volcanism, the weather. All these processes work together to destroy or deeply bury ancient surfaces and any artifacts on them.
Okay, Earth is messy.
Very messy, geologically speaking. The Moon, on the other hand, is almost the complete opposite. It's essentially geologically dead. It has no significant atmosphere, so no wind or water erosion to speak of. It has no plate tectonics.
So something landed there.
It just sits there. It might get covered by a fine layer of dust from micrometeorite impacts over millions of years, but it doesn't get ground down or subducted. If a pre-human civilization from Earth was spacefaring, even in a limited way, maybe they sent probes, maybe they established a small base, maybe even just crashed something, the wreckage or the artifacts could potentially remain on or near the lunar surface, relatively undisturbed, for literally billions of years.
It's like a planetary museum, an almost perfect time capsule just floating next door.
Exactly. The very things that make Earth habitable, its dynamic geology and atmosphere, also make it terrible at preserving its own deep history. The Moon's desolation is its archival strength.
And Mars. It's somewhere in between geologically.
Mars is less active than Earth, but more active than the Moon. It definitely has wind erosion, dust storms, evidence of ancient water flows, maybe some minor volcanic activity in the past. But crucially, it doesn't appear to have active plate tectonics like Earth does. There's no large-scale surface recycling via subduction.
So evidence might get buried on Mars, but not necessarily destroyed or melted.
Correct. If a civilization, maybe 100 million years ago, left behind structures, mining operations, maybe even waste dumps on Mars, those sites would likely get buried over millions of years by dust and sand, the slow Martian erosion. But they wouldn't be subjected to the kind of intense heat, pressure, and chemical alteration they'd face deep within Earth. They might be preserved under the Martian regolith, waiting for some future rover or astronaut to stumble upon them.
So Searching on Mars or the Moon potentially flips the script. Instead of looking for subtle, global chemical traces buried deep in Earth's rock.
You could be looking for actual, discrete, physical artifacts or structures, even if they're broken or buried. Finding even one unambiguous piece of manufactured material, one straight line where nature wouldn't make one, on the Moon or Mars, that would be monumental. It would prove either that an advanced pre-human civilization existed on Earth and went to space, or that extraterrestrial life visited our solar system long ago.
Either way, a game changer.
Absolutely. And it ties back into the broader search for alien life. Astrobiologists often focus on biosignatures, signs of life itself, like certain gases in an exoplanet's atmosphere. The Silurian Hypothesis highlights the importance of also looking for technosignature signs of technology. And paradoxically, those technosignatures might be easier to spot off-world on a quieter neighbor like the Moon or Mars than on the potentially noisy home planet itself.
It's a fascinating thought that maybe the longest-lasting, clearest evidence of a civilization isn't a pyramid or a fossil, but maybe just a discarded tool or a spent rocket stage sitting silently on the Moon for 1 billion years. The act of reaching space might be the most permanent mark a species leaves. Okay, before we wrap this up, we definitely need to touch on the pop culture side again, because as you said, the name itself comes from fiction, and it shows how these ideas sometimes bubble up in stories long before scientists formalize them. We mentioned the Silurians from Doctor Who, first appearing way back in 1970. Reptilian humanoids supposedly ruling Earth millions of years before us who went into hibernation to avoid a catastrophe.
Right, and what's interesting, as Frank and Schmidt noted in their paper, is that while it's a staple of sci-fi, they were actually kind of surprised how rarely the specific hypothesis, looking for geological traces of a past industrial civilization on Earth, had been explored rigorously in scientific literature before their work.
Yeah, it seems like such a compelling question. Why wasn't it studied more? Maybe just the sheer scale of geological time makes it feel too speculative.
That could be part of it. It's hard to get funding to look for something you strongly suspect isn't there. But the idea has appeared in other science fiction beyond Doctor Who.
They cited one novel specifically, didn't they?
Yes. James P. Hogan's 1977 novel, Inherit the Stars. It apparently features a similar premise where evidence of a pre-human spacefaring race is discovered elsewhere in the solar system, forcing a rethink of Earth's history. A classic take on the idea.
And sometimes the fictional takes get really deep into the type of evidence, not just finding artifacts.
Oh, absolutely. Larry Niven's 1980 short story, The Green Marauder, is a fantastic example of thinking about deep-time environmental conflicts.
Right, that's the one with the ancient alien recounting a plea for help from Earth's dominant life forms about 700 million years ago. What was their crisis?
Their crisis wasn't asteroids or invaders, it was biochemistry. The dominant civilization back then was anaerobic. They didn't use oxygen. Their existential threat was the rise of chlorophyll, the explosion of photosynthesis across the planet.
So, the Great Oxidation Event, from their perspective, was pollution. The rise of plants was poisoning their world with oxygen.
Exactly. It's a brilliant illustration that a civilization's major impact, its signature, might not be steel and concrete, but its interaction with the planet's fundamental chemistry. Just like our release of carbon dioxide is fundamentally altering the atmosphere today, their struggle was against the rise of oxygen. It's about metabolic footprints.
That really drives home the point about looking for chemical and atmospheric signals. And sticking with popular franchises, Star Trek also dipped into this, right?
Yes, the Voyager episode Distant Origin from 1997 is almost a perfect fictional echo of the Silurian Hypothesis's challenges.
That's the one with the Voth, the spacefaring species who are descended from dinosaurs that left Earth millions of years ago.
That's the one. And when the human crew asks the Voth scientists why there's no trace left of their advanced ancestors on Earth, the Voth explain their theory. Their ancestors likely evolved on an isolated continent that was later destroyed or drastically altered by cataclysms.
And any cities or artifacts?
Would have been obliterated, buried under oceans, ground up by erosion, or recycled by tectonic activity over the intervening millions of years. It perfectly captures the great erasure problem we discussed earlier.
So even in fiction, the biggest obstacle to finding ancient civilizations on Earth is usually Earth itself, its relentless geological processes. The need to look for subtle, indirect chemical ghosts seems almost inevitable, whether in science or sci-fi.
It really reinforces the core idea. The planet's dynamism is both life-giving and history erasing. #outro.
So after this deep dive into searching for geological ghosts, What's the main takeaway for you, the listener? What does this all really mean?
I think the fundamental point is that the Silurian hypothesis, while framed as looking for the past, is actually an incredibly powerful tool for understanding the present and the future. It's about understanding the Anthropocene.
How so?
By forcing us to define, with real scientific rigor, what the long-lasting geological signature of an industrial civilization is, we are simultaneously defining the signature that we are creating right now.
Ah, right. All the things we talked about. Looking for the rapid carbon spikes, the weird isotope ratios like 2,244, the nitrogen cycle disruptions, the plastic layers, the potential geothermal traces. Those aren't just hypothetical markers of some past civilization.
They are literally the markers we are actively embedding in the geological record at this very moment. We are creating that sharp carbon spike. We are making technofossils. We are altering global chemical cycles. We are producing isotopes like plutonium-244. We are, in effect, creating the very Silurian evidence that Frank and Schmidt proposed looking for.
So studying this hypothetical past helps us understand the true permanence, or lack thereof, of our own impact.
Exactly. It gives us profound perspective. Our entire civilization, with all its complexity and technology, has existed for such a tiny, tiny fraction of Earth's history. Yet in that geological blink of an eye, we've managed to create a disturbance that might be detectable in some form for potentially hundreds of millions of years. It highlights both our power and our transience.
The sheer difficulty of finding evidence from, say, 55 million years ago really underscores how vast geological time is and how fleeting even our most impressive structures will likely be on that scale. But our chemical waste, that might be another story.
Our waste, our chemical alterations, our isotopic signatures, those might be our longest-lasting legacy written into the rock itself.
Which leaves us with a final provocative thought for you to ponder. We know that even these powerful markers, plastics, Pu-244, chemical anomalies, will eventually degrade, decay, dilute, or get recycled deep into the Earth's mantle over immense timescales. Given the planet's relentless capacity for erasure, what single trace from our current human era, perhaps something very localized but incredibly resistant, will be the absolute last thing to disappear from the geological record? Could it be the altered rock deep within a geothermal well? Maybe the vitrified, stable core of a deep geological nuclear waste repository? Or perhaps something surprisingly small and simple, like a synthetic diamond created in a lab today, buried by chance, resisting heat and pressure for potentially billions of years? What will be the final fading echo of our entire, complex, technologically advanced, yet ultimately fleeting civilization? We'll leave you with that thought.
Welcome back to The Deep Dive. Today we're tackling, well, a really heavy topic. It's ancient, it's deeply polarizing, and profoundly consequential: capital punishment.
Also known as the death penalty.
Right. And this isn't just some abstract legal question, is it? It's a genuine global conflict over human rights, ethics, and really the very definition of justice itself.
It absolutely is. And we have to approach this deep dive with, the seriousness it really demands. Our sources are clear. At its core, capital punishment is the state-sanctioned killing of a person as punishment for some crime, whether they actually did it or were just alleged to have.
And historically, they didn't mince words, did they?
No. The term used was stark: judicial homicide.
Wow. And even the term capital punishment, that's more literal than most people probably realize.
It is. It takes us right back to the ancient world. Capital comes from the Latin word caput,
which means
head. Simple as that. It originally referred pretty directly to the main form of execution back then: beheading. Obviously, methods have changed drastically in some places, but the core idea, taking the head, taking the life, that's still the root of the term we use today.
Okay, so before we dive deep into the history, let's maybe get a snapshot for the listener. Where does this practice stand globally right now? Because the numbers, well, they paint a really complicated picture.
They really do. The world is profoundly fractured on this. As of 2021 data, you have 56 countries that officially retain capital punishment. They actively authorize its use.
56, okay.
But here's the kicker, the statistical paradox that makes this so complex. While 111 countries have abolished it, de jure meaning completely in law.
Which sounds like a clear majority.
It does, number of countries wise. but over half of the world's entire population lives in those countries where the death penalty is still retained.
Ah, right, because you've got huge population centers like China and India still in the retentionist camp. That skews the population statistic massively, even if the number of abolitionist countries is growing.
Precisely. And if you zoom in on, say, the developed world, the picture gets even clearer. Among the 38 OECD members, that's the Organization for Economic Cooperation and Development, basically the highly developed economies,
Yeah.
only 2 still retain capital punishment. Just 2.
The United States and Japan.
That's it. The consensus among Western, democratic, developed nations has overwhelmingly shifted towards getting rid of it.
So our mission today, then, is to try and unpack this deep division. We're going to trace the long and often brutal history of this ancient practice.
We'll look at the modern movements pushing for abolition globally.
We'll dissect the, frankly, surprisingly vast range of crimes that still carry the death penalty in some places today.
And crucially, we need to analyze the intense controversies, the ethics, the human rights arguments, and that constant, terrifying risk of irreversible error.
Right. The fear of getting it wrong. Let's start at the beginning, then. The shift from, say, tribal justice to modern states seems pretty key here.
It really is. That takes us nicely into our first major section, the deep history. We're talking about a journey from blood feuds, regulated revenge, all the way up to the Enlightenment's big rethink.
This is genuinely one of the oldest forms of societal control we have, isn't it?
Absolutely. Execution has been a feature of, well, virtually all civilizations since recorded history began. And for thousands of years, you have to remember, it wasn't always about moral retribution in the way we might think of it now.
More about practicality.
Often, yes, practical necessity. Our sources remind us that before the 19th century, before we really invented modern state-funded prisons as we know them,
Yeah, what did societies do?
well, capital punishment was frequently the only immediately workable way a society felt it had for permanent deterrence, and crucially, incapacitation of people seen as serious threats. There just weren't many other options for long-term removal.
And before organized state courts, justice was much more local, community-driven.
Exactly, decentralized, often dictated by the community that felt wronged. These early punishments relied a lot on balance and compensation.
Like blood money.
Yes, early on we see blood money compensation,
Yeah.
where an offender's family would pay the victim's family to sort of head off further retaliation, prevent a feud.
But sometimes that wasn't enough.
Right. For crimes seen as too severe for just money, societies often regulated things like blood feuds or vendettas. But these weren't always just chaotic revenge cycles. Early assemblies, like the Norse things, for example, provided structured places to manage these disputes, try and reach a resolution.
And the concept of responsibility back then was different, wasn't it? Not always about the individual who actually did the deed.
No, because justice was fundamentally tribal or group-based, not strictly individual. Your identity was tied up in your clan, your family. If a serious crime happened, the debt was owed by the perpetrator's group to the victim's group.
So if a settlement demanded a life,
Then the person executed didn't necessarily have to be the original perpetrator. They just needed to be someone from the offending group whose death would satisfy the debt, restore that balance between the clans.
wow. Okay, so moving into actual written laws, you have the Code of Hammurabi around 1700 BC. That institutionalized capital punishment, right, but not equally.
It formalized that eye for an eye idea, but with a huge caveat. The punishment wasn't just based on the crime. It explicitly depended on the social class, the standing, the group identity of both the victim and the perpetrator.
So justice was stratified from the get-go.
Absolutely. The life of a noble was valued differently than a commoner or a slave, and the punishment or the compensation required reflected that hierarchy.
Then we jump forward to ancient Greece, and there you see this incredible ideological swing in a fairly short time, right? Draco and Solon.
Yeah, that's a fascinating contrast. Draco, around 621 BC, his contribution was applying the death penalty incredibly broadly, almost universally for serious crimes, and even for many quite petty ones.
That's where draconian comes from.
Exactly.
Yeah.
His code was so notoriously severe, it gave us that word, meaning excessively harsh. It really showed a state view where almost no crime was too small for the ultimate penalty.
But then Solon came along and just reversed course.
Pretty much. He repealed almost all of Draco's code. It was a very early example of putting limits on state power. Solon kept capital punishment, but only for intentional homicide. And even then, his laws often required the victim's family to actually agree to the execution, showing that lingering sense of community satisfaction being important.
And the Greek philosophers then tried to build the why behind it all, the philosophical justifications, arguments we still hear echoes of today.
For sure. You see this really interesting contrast between Protagoras, Plato, and Aristotle. It's like a foundational lesson in thinking about punishment.
Except Protagoras.
He was more utilitarian. He argued revenge is kind of pointless because you can't undo the harm. So if the state is going to use capital punishment, it has to be purely for the future good, protecting society, or deterring others. Strictly pragmatic.
Okay, execute only to prevent future bad acts. How did Plato see it?
Plato was much more, let's say, spiritual or ethical about it. He saw a serious crime, especially murder, as a kind of defilement, almost a disease of the soul.
A disease.
Yeah. So for Plato, capital punishment wasn't just about deterrence, it was about purification. A last resort, mind you, only if the crime was so bad that rehabilitation seemed impossible. It was like a moral cleansing for the community and maybe even, strangely, for the soul of the person being executed.
And Aristotle, he brought it back to individual responsibility.
Exactly. Aristotle connected punishment directly to free will and accountability. He argued that because people choose their actions, they're responsible. So a judge's job was to find a penalty that would effectively annul the crime by compensating for the injury caused.
And for murder.
He concluded that if the crime was the deliberate taking of a life, no penalty short of taking the murderer's life could truly compensate or annul that act. That really laid the groundwork for the modern idea of proportional retribution, an eye for an eye, but philosophically justified.
And that framework got picked up widely by ancient Rome, often with, well, extreme brutality.
Oh, absolutely. The Roman 12 tables listed capital punishment for things like libel, arson, even theft. But the ultimate symbol of Roman state power and cruelty has to be crucifixion.
Which wasn't just about killing someone.
No, it was about public humiliation, spectacle, terror, usually reserved for slaves, rebels, traitors. It was deliberately designed to maximize suffering, sometimes taking days for the person to die, and their bodies were often left hanging as a grim political warning.
That detail, the duration of suffering, it really underscores how torturous pre-modern execution often was. But you mentioned a fascinating exception in China.
Yes, the Tang Dynasty under Emperor Xuanzong is a really interesting counterexample. Between 747 and 759 AD, so for about 12 years, he actually abolished the death penalty entirely.
Really? What do they do instead?
Substituted it with punishments like severe whipping or exile. It was a remarkable, though short-lived, experiment. It only ended when the huge upheaval of the Andalusian Rebellion made restoring order seem impossible without bringing back the ultimate penalty.
And even when they did use execution, their cultural preferences were quite different from the West, weren't they?
Very much so. There was a strong cultural preference for strangulation over beheading.
Why was that?
It seems trivial, but it's deeply significant. Traditional Tang beliefs held that your body was a gift from your parents. Beheading was seen as dishonoring your ancestors because you couldn't return the body intact to the grave. It shows how even within a society that uses capital punishment, deep cultural values can shape how it's done.
That idea of respecting the body seems completely absent when you look at the methods used elsewhere in pre-modern times. They were just instruments of terror.
Pretty much. The list is horrifying and designed for public agony and spectacle. You had the breaking wheel, designed to shatter bones before death, keel hauling in maritime contexts, impalement, burning at the stake.
The hanging, drawing, and quartering in England.
Notorious, yes. And towards the end of the Tang Dynasty, they used the truly horrific, slow slicing, Ling Chi, sometimes called death by 1,000 cuts. These weren't just punishments. They were terrifying public performances of state power.
Okay, so this era of state-sanctioned torture finally starts to crack with the Enlightenment in the 18th century. What was the big shift in thinking?
The focus moved quite radically. It shifted away from the medieval idea of expiation-like, the state needing to perform a spiritual cleansing, towards the more rational concept of the social contract.
Meaning punishment had to be useful.
Exactly. Enlightenment thinkers argued punishment couldn't just be about religious retribution anymore. It had to be rational and critically useful to society. Its main goals became deterrence and protection, not settling some kind of spiritual debt.
And this utilitarian thinking provided the first real intellectual case for abolition.
Absolutely. The landmark work here is Cesare Beccaria's treatise from 1764 on crimes and punishments. Beccaria systematically argued for abolition. He said the death penalty was state power abused. It was unnecessary for protecting society, and fundamentally unjust.
Jeremy Bentham, too, right? The utilitarian philosopher.
Yes, Bentham followed suit, arguing that if a penalty didn't demonstrably serve a useful purpose for society, it should be abolished.
And they found a pretty major flaw in the whole idea of public executions being a deterrent.
They did. Thinkers like Beccaria and later people like Charles Dickens and Karl Marx, they observed something really disturbing, kind of counterintuitive. Violent crime and general public disorder often seem to increase right at the times and places where public executions were happening.
So they weren't solemn warnings, they were spectacles.
Exactly. They became occasions for drunkenness, theft, general chaos, not quiet reflection. This observation was crucial. It led officials to realize public executions were actually counterproductive. And that led to the big decision to move executions behind prison walls, out of public view. That really marks the beginning of the modern, more hidden application of capital punishment.
Moving it behind walls didn't end the debate, though. That shift sets us up perfectly for Section 2, the modern divide. This is where the world really starts splitting into those retentionist and abolitionist camps we see today.
And that Enlightenment critique had immediate effects. Inspired directly by Beccaria, the Grand Duchy of Tuscany under Grand Duke Leopold II became the very first state in modern history to abolish the death penalty. That was in 1786.
1786, that's huge. A real turning point. Who followed?
We see movement pretty quickly, especially in the Western Hemisphere. The Kingdom of Tahiti's assembly abolished it in 1824, swapping it for banishment. Venezuela abolished it in 1863. That was a really key moment for Latin America. San Marino followed in 1865.
And in the U.S.?
Michigan was the pioneer state, banning it way back in 1846. So these early adopters really showed it was possible for a modern state to function without state killing.
But the real global momentum, the big wave of abolition, that came after World War II, didn't it? What drove that?
I think the horrors of the war really exposed the dangers of unchecked state power and maybe underscored the fragility of basic human rights. Many countries that were transitioning away from authoritarian regimes, moving towards democracy, saw abolishing the death penalty as a really important symbolic break from their oppressive pasts.
And international pressure played a role, too.
A huge role, particularly regional bodies like the European Union. The EU made abolition a non-negotiable requirement for membership. It's right there in their Charter of Fundamental Rights today. That political pressure has been incredibly effective in making Europe virtually capital punishment free.
Okay, so let's recap the current global count. Using 2022 data, where do things stand now?
It's still divided, definitely. But abolition is clearly the dominant trend globally in terms of the number of countries. You've got 54 countries that actively retain it.
Okay, 54 retentionists.
To compare that to 112 countries that have abolished it completely in law for all crimes. Plus, there are another 7 that only keep it for really exceptional circumstances, like wartime crimes. And 22 more that are considered abolitionist in practice. They haven't executed anyone for at least 10 years, even if it's still technically on the books.
And geographically, where are those 54 retentionist countries concentrated?
Overwhelmingly, they're in Asia, the Middle East, Africa, and the Caribbean. Europe stands out as the most uniformly abolitionist region.
With one very notable, very political exception.
Belarus, the only country in Europe that still actively carries out executions.
And Belarus is actually moving in the opposite direction, aren't they? Tightening its use.
Exactly. Reflecting a completely different political climate. President Lukashenko recently signed a law actually expanding the death penalty to include high treason if committed by officials or soldiers. Human rights groups tend to see this as a tool primarily aimed at intimidating potential opposition within the state itself, which is obviously a stark contrast to the global trend.
Let's talk about the execution numbers themselves, using that 2022 Amnesty International data. Because the disparity is just staggering, isn't it? It shows that a tiny handful of countries are responsible for almost all the world's executions.
It's possibly the most shocking data point in this whole discussion. China remains by far the world's biggest executioner. The exact number is a state secret, but estimates consistently put it at over 1,000 executions per year, maybe significantly more.
Over 1,000. And after China?
Iran executed over 576 people in 2022. Saudi Arabia executed 196. Those 3 alone account for the vast majority of known executions.
And how does that compare to the developed countries that still retain it, like the U.S. and Japan?
The scale is just completely different. The U.S. executed 18 people in 2022. Japan executed 1. So while the U.S. and Japan are ethically and politically aligned with that minority retentionist view, the sheer volume of executions is exponentially smaller than what you see in places like China, Iran and Saudi Arabia.
And per capita rates can be revealing too, right?
Absolutely. Past analyses have often pointed to countries like Iran and Singapore as having disturbingly high execution rates relative to their population size. It underscores just how central the death penalty is to their judicial systems.
It's also crucial to remember this isn't always a one-way street towards abolition. Countries can and do resume executions after stopping.
Pakistan's is the most prominent or recent example of that. They had a moratorium for 6 years, but then the government lifted the ban in December 2014.
Why? What triggered that?
It was a direct response to the horrific Peshawar school massacre, where 149 people, mostly children, were killed by terrorists. The massive public grief and outrage, the demand for immediate severe justice against terrorism led them to restart executions. And since then, they've executed over 400 people. It just shows how a major national trauma can quickly reverse years of political restraint.
That brings us right into Section 3. The sheer breadth of crimes that can still carry the death penalty. It's really not just for the worst of the worst murders anymore, is it?
Not at all. When you look globally, it's used to enforce a huge range of state boundaries: economic, political, moral. Of course, intentional homicide is still the core traditional capital crime, often requiring aggravating factors, like murdering a child using torture, multiple victims, terrorism.
What about things like war crimes or genocide? Historically, those often led to execution.
They did. Think Nuremberg after WWII. But that's a major area where international law has evolved significantly. Modern international courts, like the International Criminal Court, the ICC, or the Tribunal for the former Yugoslavia, they explicitly forbid the death penalty.
So even for the absolute worst crimes against humanity?
Even then, the sentence is life imprisonment. There's now a global consensus, at least in international law, that even those convicted of the most heinous acts shouldn't forfeit their fundamental right to life.
Okay, so let's look beyond homicide. Drug offenses seem to be one of the most common nonviolent crimes carrying the death penalty.
They are. At least 35 countries, mostly in Asia and the Middle East, retain it for drug trafficking, sometimes even possession or dealing. This includes major execution states like China, Iran, Singapore, Malaysia. These countries often frame drug crime not just as a social problem, but as a grave threat to national security and stability.
But even within those systems, we're seeing some legal shifts, especially in Southeast Asia, away from mandatory sentences.
Yes, that's a really interesting development. Singapore changed its laws back in 2013. They introduced judicial discretion for drug couriers, meaning it's not an automatic death sentence anymore if they meet certain criteria, like if they cooperate with authorities or if they have some kind of diminished mental capacity.
And Malaysia went further recently.
They did in 2023. Malaysia abolished the mandatory death penalty for all drug crimes. The death penalty itself still exists as an option, but now the judge has the discretion to impose a different sentence, like life imprisonment. It's a significant move towards less rigidity.
China's use of capital punishment goes way beyond drugs, though, right? Into economics and politics.
Oh, definitely. China uses it for serious cases of corruption, major financial crimes, even human trafficking. It underscores the state's view that economic stability and protecting state assets are paramount, justifying the ultimate penalty.
And political crimes. Treason, espionage.
Those are almost universally capital offenses in countries that retain the death penalty. They're seen as the ultimate betrayal of the state, the final line of defense for sovereignty.
We saw a very political example of that recently concerning Taiwan.
That's right. In 2024, China issued a new judicial order stating that promoting Taiwan independence could, in the most severe cases, be punishable by death. Now, practically enforcing that against someone in Taiwan is almost impossible due to jurisdiction issues.
But symbolically?
Symbolically, it's huge. It demonstrates using the threat of the death penalty as a high-level political deterrent and a very clear signaling tool.
And then the list gets even wider when you look at crimes related to morality or religion, especially under legal systems like hudud or qisas.
This is where the list really diverges sharply from, say, Western legal ideas. Hudud crimes are seen as offenses against God. Qisas involves retribution. So in some jurisdictions, you see the death penalty for things like aggravated rape, certainly, but also sodomy, even bestiality.
Religious crimes, too.
Yes. Things like apostasy, formally renouncing the state religion, or blasphemy can be capital offenses in countries like Pakistan, Iran, Saudi Arabia. You also see things like witchcraft or sorcery listed as capital crimes in Saudi Arabia.
It's quite a list. Drinking alcohol in Iran.
In certain circumstances, yes. Unlawful sexual behavior, kidnapping in some places, even specific U.S. states like Georgia and Idaho technically retain it for kidnapping, as does Singapore.
So when you add it all up from genocide and treason down to financial corruption, drug trafficking, apostasy, even drinking alcohol, it really highlights that capital punishment today isn't just a response to horrific violence. It functions more like a flexible tool for states to rigidly enforce whatever their specific political, economic, or moral red lines happen to be.
Exactly. It's as much a reflection of state sovereignty and control as it is about the crime itself.
Okay, let's pivot now into the heart of the controversy, Section 4. We really need to explore that core philosophical clash and the very practical arguments about human rights, error, and bias. Let's start with retribution versus human rights.
Retribution is still the bedrock moral argument for supporters. You have philosophers like Immanuel Kant who basically argued that taking a life is unique. No other penalty can balance the scales for murder. So the murderer must die. It's a moral imperative.
And modern supporters echo that.
Yes, people like Professor Robert Blecker argue strongly for punishment that is truly proportional, even if it's painful. They emphasize focusing on how heinous the crime was, not necessarily on making the execution comfortable or easy. It's about justice for the victim, in their view.
But the abolitionist movement comes at it from a completely different angle, challenging the state's right to kill at all.
Fundamentally, the abolitionist view, championed by groups like Amnesty International, frames capital punishment as the ultimate violation of human rights, especially the right to life, obviously, but also the right to be free from torture or cruel, inhuman, or degrading treatment. They argue the state loses its moral high ground when it uses the same violence it condemns.
Albert Camus had a particularly powerful argument about the psychological aspect, didn't he? The waiting.
He did. Camus argued that execution is fundamentally different from just dying because the state inflicts this prolonged psychological torture. The condemned person has to wait, sometimes for months, often years, knowing exactly how and when their horrifying death will occur.
What was his analogy?
He said for an execution to be truly equivalent to the victim's death, the killer would have had to warn their victim months ahead, kept them confined, told them the exact date and method of their death. And he argued such a monster is not encountered in private life. Therefore, the state's calculated, premeditated killing becomes disproportionately cruel.
That kind of psychological torture argument was central to the huge international outcry over Naganthran Dharmalingam's execution in Singapore in 2022.
That case really captures the tension perfectly. Dharmalingam was executed for drug trafficking, but activists globally argued against it because he had a certified low IQ, 69, and clear signs of cognitive impairment. The whole debate was whether his mental state should exempt him under international human rights standards.
But the Singapore courts disagreed.
They did. They maintained that while his functioning might be borderline, he still had enough capacity to understand his actions and the consequences. So, under Singaporean law, he was considered fully accountable and the execution proceeded. It highlights that clash between international human rights norms and national legal sovereignty.
And this inherent tension, this potential for disagreement or error, leads us straight to maybe the most powerful practical argument against it, the problem of irreversible error.
This is the absolute core pragmatic flaw, especially in democratic societies that value due process. Once an execution is carried out, it can never ever be undone. If you later find out the person was innocent, there's nothing you can do.
The Timothy Evans case in the UK is a classic, tragic example.
Hauntingly so. Evans was executed in 1950 for murders at his residence. It was later proven, beyond doubt, that his landlord, John Christie, was the actual serial killer. Evans was innocent. That wrongful execution was a massive factor in strengthening the abolition movement in the UK, leading to abolition there.
And in the US, the risk of executing the innocent isn't just a historical footnote, is it? The data suggests it's a real ongoing danger.
The numbers are just horrifying. As of 2017, 159 people who had been sentenced to death in the U.S. were later exonerated. Freed from death row, often due to DNA evidence or other proof of innocence emerging years later.
159 exonerations.
Yes. And most legal experts agree that number is so high, it's virtually certain, statistically speaking, that innocent people have been executed in the U.S. without ever having their innocence proven before it was too late.
Beyond outright innocence, you also mentioned procedural issues in some places that might increase the risk of error, like in Singapore's drug laws.
All right. Amnesty International has raised serious concerns about Singapore's Misuse of Drugs Act because it contains legal presumptions that effectively shift the burden of proof. For example, if you're found with the key to a place where drugs are stored, the law might presume you possessed those drugs, and then it's up to you to prove you didn't.
Oh, which flips the usual legal standard.
Completely. It conflicts with the fundamental principle that the prosecution must prove guilt beyond a reasonable doubt. These kinds of presumptions, while maybe legally efficient, inherently increase the risk of convicting someone, potentially even sentencing them to death, based on circumstance rather than direct proof.
Another deeply troubling aspect is the persistent evidence of bias, racial, religious, socioeconomic, in who actually ends up on death row.
The evidence, particularly on racial bias in the U.S., is stark and undeniable. Multiple studies have shown that defendants whose appearance is perceived as more stereotypically black are statistically more likely to receive a death sentence, especially if the victim was white. This isn't just about who commits crime. It suggests a systemic bias where race influences the ultimate judicial outcome.
There was also that case about religious bias, Dominique Ray in Alabama.
Yes, in 2019, Ray was Muslim. As his execution approached, he asked for his imam to be present in the execution chamber for spiritual support. The state offered its standard Christian chaplain, but initially denied his imam. They cited the late timing of the request, but the courts eventually intervened, though it was a very close legal battle. Critics argued forcefully that denying him his chosen spiritual advisor in his final moments was a clear violation of religious freedom and neutrality principles.
And socioeconomic status often plays a huge role too, right? In terms of who gets adequate defense, the circumstances leading to the crime, like the Abdul Kahar Othman case in Singapore.
Othman's case, also executed in 2022, really highlighted this. He was Malo Singaporean from a poor background, struggled with drug addiction his whole life, basically cycling in and out of prison. Activists argued his case was a prime example where rehabilitation and social support were needed, not the finality of execution. It shows how poverty and lack of opportunity can intersect with harsh sentencing laws, especially mandatory ones.
Finally, let's touch on the methods themselves. There's been this long search for a humane way to execute, hasn't there? From the guillotine to the electric chair, gas, now lethal injection in the U.S.
Lethal injection was intended to be the answer. To provide a seemingly clean, medical, pain-free death. Give the whole process a veneer of, well, clinical detachment.
But the reality has been quite different.
Very different. The data shows the search for a truly humane method might be fundamentally flawed. One major study looked at U.S. executions from 1977 to 2001 and found that in about 4.5% of cases, there were significant unanticipated problems or delays that caused what appeared to be unnecessary agony for the prisoner. Botched executions.
And the drug combination itself has been questioned scientifically.
Yes, a really important study in The Lancet back in 2005 looked at toxicology reports from lethal injection cases. It found that in 43% of the cases they analyzed, the level of the anesthetic the drug meant to knock the person out first was insufficient to guarantee they were actually unconscious when the subsequent paralytic and heart-stopping drugs were administered.
Meaning they could have been awake but unable to move or cry out.
Exactly. Potentially experiencing suffocation and extreme pain while fully conscious but paralyzed.
Yet, despite all this evidence of potential pain and problems, the U.S. Supreme Court has consistently upheld lethal injection as constitutional.
They have. In key cases like Bays v. Rees in 2008 and Glossop v. Gross in 2015, the court essentially ruled that the Eighth Amendment's ban on cruel and unusual punishment doesn't guarantee a completely painless death. It mainly prohibits punishments that are deliberately designed to inflict gratuitous pain or suffering. They've argued that lethal injection, even with its documented flaws and risks, doesn't meet that high threshold for being unconstitutional.
Okay, let's move to our final section. Looking at specific groups like juvenile offenders and the broader international legal momentum. First, the age question. International law seems pretty clear here.
It is. The UN Convention on the Rights of the Child explicitly forbids imposing capital punishment on anyone who's under 18 years old when they committed the crime. It's a very clear international standard.
Yet it's still violated.
Yes. Since 1990, 10 countries are known to have executed juvenile offenders. That list includes China, Iran, Pakistan, Saudi Arabia, Sudan, Yemen, and historically the United States.
Iran has been particularly prominent in this, haven't they?
Tragically, yes. Before they changed some controversial laws in 2012, Iran was responsible for about 2/3 of all known juvenile offender executions worldwide. Their previous system used the lunar calendar and interpretations of Islamic law to set the age of full criminal responsibility as young as 9 for girls and 15 for boys in some cases.
And have things changed there?
The laws have technically changed to allow judges more discretion for minors, but reports of juvenile executions, while fewer, still surface. It shows that ongoing tension between international norms and specific domestic legal interpretations.
And the U.S., while on that list historically, has now stopped the practice.
Yes, thanks to the Supreme Court. They abolished it in two main steps. First, for offenders who were under 16 at the time of the crime, back in 1988. Then in 2005, the landmark Roper v. Simmons decision abolished it for all juvenile offenders, anyone under 18.
What was the reasoning?
The court recognized that adolescents fundamentally lack the same level of maturity, judgment, and impulse control as adults due to their still developing brains. They're more vulnerable to peer pressure. Therefore, executing them was deemed disproportionate and violated the constitutional ban on cruel and unusual punishment.
Looking bigger picture now, what are the main international forces pushing against the death penalty? Those UN resolutions seem important.
They are significant, yes. The UN General Assembly has passed resolutions starting in 2007 calling for a global moratorium on executions, with the ultimate aim being total abolition. Crucially, these resolutions are non-binding, meaning countries don't have to follow them.
But support is growing.
Steadily. In 2022, 125 countries voted in favor of the moratorium resolution. That clearly shows a growing international consensus against the practice, at least at the policy level.
Although some powerful nations consistently dissent.
That's the counterpoint. The resolution isn't unanimous. Major powers like the United States, China, Iran, North Korea consistently vote against it or abstain. Their opposition really highlights how deep the political and cultural divisions on this issue remain.
Regionally, though, the EU's influence is undeniable.
Absolutely. The EU is arguably the most effective abolitionist force globally. As we said, banning the death penalty is a strict requirement for membership. The Council of Europe also works tirelessly on this. The result is that Europe is effectively a death penalty-free zone, apart from Belarus. That kind of political and economic leverage has been very effective, for example, in pushing countries like Turkey towards abolition when they sought closer ties with Europe.
And we are still seeing countries abolish it, right? It's not a static picture.
No, the trend continues. Kazakhstan abolished it fully in 2021. And just this year, 2024, Zimbabwe abolished the death penalty.
Yeah.
These moves, often after many years of having a moratorium in place, reflect that growing international pressure and the increasing difficulty for states to morally and legally justify retaining it within a modern human rights framework.
But policy change often seems to lag way behind public opinion, doesn't it? Especially in countries that have abolished it.
That's a huge point. Public support for the death penalty often remains stubbornly high, even in abolitionist nations. You mentioned Taiwan earlier. 88% of the public there consistently disagree with abolition, polls show. In the U.S., support for it in murder cases was around 55% in 2020, and it tends to fluctuate with crime rates and high-profile cases.
And what happens if an abolitionist country experiences, say, a major crime wave or a terrorist attack?
You often see calls for reintroduction flare up dramatically. Polls in places like South Africa, Brazil, where support for bringing it back hit 57%, or even Canada, where 54% supported its return in some recent polls, they demonstrate this dynamic. The public, often driven by anger, fear, and a desire for retribution after shocking events, can quickly demand the ultimate penalty, even if the government and the courts remain committed to abolition on principle.
What a journey we've taken. From ancient tribal necessity through eras of brutal spectacle and class-based justice, then the Enlightenment's moral challenge. Today, it's clearly a practice in global decline, pushed back by human rights concerns, international pressure.
Yet it's still retained by countries where over half the world's population lives. And it's used for the surprisingly broad, often politically charged, range of crimes far beyond just murder.
The core tension seems to be right there.
I think the death penalty really acts as a kind of litmus test for a society's deepest priorities. It's retreating where the focus is on human rights, the possibility of error, the inherent dignity of life, but it remains fiercely defended and used where state control, absolute moral certainty, or the public's raw demand for final retribution in the face of violence holds more sway than the risk of getting it wrong.
Which brings us perfectly to our final provocative thought for you, the listener. When you consider the devastating documented history of wrongful executions, people like Timothy Evans, the 159 exonerated from U.S. death rows, and add to that the scientific evidence of botched lethal injections causing potentially extreme agony, does the continued use of the death penalty, even in our most modern, sophisticated legal systems, inherently mean we're choosing to prioritize the idea of final retribution over the absolute non-negotiable certainty of justice? Welcome back to the deep dive. If we were to play a word association game and I said the word genius, I think for almost everyone, one image immediately flashes into your mind.
It's always Albert Einstein.
Always. He's the ultimate symbol of, supreme intelligence. The scientific icon, the wild hair, the Nobel Prize, and of course the world's most famous equation, E equals mc².
Right, and that iconic image, the gentle, sort of eccentric old man who became Time's Person of the Century, it's so powerful that it almost sanitizes the real person.
Mm.
So our mission today, using the stack of sources you provided, is to get a kind of complete shortcut. We want to move beyond that legend and into the contradictory, complex heart of this scientific revolutionary.
To really understand the journey.
Exactly.
Yeah.
The journey of a man whose influence wasn't just in physics, but in politics and culture, everything.
And what we found right away, just drilling into the earliest parts of his career, are these profound ironies that completely redefine what you might think of as a traditional academic genius.
Absolutely. And the first irony is, well, it's geographical, it's institutional, the foundational theoretical breakthroughs of the entire 20th century.
The papers that changed everything?
Yes. Our whole understanding of space and time, they weren't conceived in the halls of some prestigious European university.
So where did they come from?
They were developed while Einstein was serving as an assistant examiner at the Swiss Patent Office. He was clocking in for a 9-to-5 job.
That seems impossible. The greatest mind of the century stuck evaluating, what, gravel sorters?
It's incredible.
Yeah.
And the second irony, and this one really captures the maybe tragedy of his later career,
Yeah.
is that he was instrumental in kicking off the quantum revolution with his work on light, yet he spent the last phase of his life, nearly 3 decades, locked in this ferocious and ultimately unsuccessful battle against the very quantum theory he helped create.
Okay, let's unpack this. When we talk about scientific prodigies, we usually expect this, clear story of early, effortless brilliance. But our sources show a surprisingly slow start for Einstein.
It's the first real nugget of surprise, isn't it? When he was very young, his parents were genuinely worried about his intellectual development.
Ugh.
He was so slow to learn to talk that they actually consulted doctors. They worried he had some kind of learning disability. It just flies in the face of this popular image of a genius born, fully formed.
It really does. It paints a picture of a more contemplative child, maybe someone who's internalizing the world instead of just quickly outputting language.
I think so.
Yeah.
And then, at age 5, something clicks. Something tangible happens that sets him on his lifelong path.
The compass moment.
That's the one. He was sick in bed, and his father, Hermann, brought him a simple magnetic compass. And seeing that needle constantly turning back to the same unseen force, the magnetic field, Einstein described it as this profound, almost spiritual experience.
Wow.
It sparked his fascination with electromagnetism, and critically, it gave him this lifelong conviction that reality was governed by hidden, unseen laws. He later said that moment confirmed for him that something deeply hidden had to be behind things.
That's the birth of the theoretical physicist right there. The search for that underlying structure.
Exactly. And once that foundation was laid, the speed of his intellectual growth was just astonishing, though it was largely self-directed.
Right. He wasn't just a good student.
Not at all. By age 12, he wasn't waiting for school anymore. He was rapidly teaching himself advanced mathematics. We're talking algebra, calculus, the whole 9 yards.
He taught himself calculus at 12.
He was so deep into Euclidean geometry that before he even turned 13, he had devised his own original proof of the Pythagorean theorem. By 14, he'd mastered integral and differential calculus.
So this wasn't just memorizing things. This was a mind capable of independent, foundational mathematical thought before he was even a teenager.
Precisely. And it wasn't just math. You mentioned that his approach to physics was always philosophical. Where did that come from?
That's a great question.
It started early, thanks to a family friend, a medical student named Max Talmud, who tutored him. At 13, Talmud introduced him to philosophy, including one of the most notoriously complex works out there, Immanuel Kant's Critique of Pure Reason.
Kant is not exactly light reading for anyone, let alone a 13-year-old.
Far from it. Yet Talmud noted that Kant's works, which he described as incomprehensible to ordinary mortals, seemed clear to the boy. And this is so vital because it shows that Einstein's drive was never just technical.
He wasn't just solving for X.
No, he wasn't satisfied with how things moved. He wanted to understand the deepest possible coherence, the preconditions of knowledge, the absolute laws governing existence. It was a philosophical bedrock that would later define his whole life's work. He was always searching for that internal logical elegance.
And while he's still a teenager, we see the first signs of his political and sort of anti-authoritarian streak.
Yes, that came in 1896. He was just 16. He formally renounced his German citizenship. He was from the Kingdom of Württemberg at the time, specifically to avoid mandatory military conscription.
So he became stateless.
For several years, yes, until he acquired Swiss citizenship in 1901. And that early rejection of nationalism and militarism was a clear sign of the lifelong pacifist and internationalist he would become.
So we have this intellectual powerhouse, a mind that's reforming calculus and philosophy before adulthood, graduating from a top school in Zurich. You'd think, okay, straight path to a professorship.
Well, that's not what happened at all.
No.
And this is where the irony really deepens. Because of personality conflicts, maybe some poor recommendations from his professors, he just couldn't get an academic job. He drifted, taught for a bit, until a friend's father helped him get a position in Bern.
At the Swiss Patent Office.
As an assistant examiner. He worked there from 1902 all the way to 1909.
I mean, we know now he was secretly about to revolutionize physics, but what was his actual day-to-day job like? Was it really that mundane?
His official job was to evaluate the feasibility of inventions, everything from electric typewriters to gravel sorters. But here's the unexpected intellectual gift of that job. His work often involved evaluating inventions related to electrical machinery, signal transmission, and crucially, new methods for the synchronization of clocks across long distances.
Synchronizing clocks, that is the absolute core of the problem that special relativity had to solve, the definition of simultaneity.
Exactly. To decide if an invention was actually new, he had to constantly perform these rigorous Gedankenexperimente thought experiments about how observers, moving relative to each other, would perceive signals and, most importantly, time. His job forced him to wrestle with these issues of relative motion and simultaneity.
That's incredible. So the mundane, financially stable job at the patent office, far from the pressures and dogma of university life, actually gave him the perfect unintentional lab for special relativity.
It gave him the time, the focus, and the right kind of problems. He was assessing reality through these practical physics puzzles about time and motion, which forced him to question the definitions that everyone else just took for granted.
Yeah.
He called it his bread and butter job, but that very setup allowed his revolutionary ideas to grow untainted by the academic pressures he really disliked.
And this hidden intellectual development leads to one of the most astonishing periods in the history of science. 1905, his Annus Mirabilis, the miracle year. A 26-year-old patent clerk publishes 4 revolutionary papers. That level of output is, it's almost unthinkable.
It genuinely stands as one of the great milestones in intellectual history.
Yeah.
The only real comparison in scope and impact is maybe Isaac Newton's work during the plague years. And you have to remember, he did all this while holding down a full-time job and raising a young family.
Okay, so let's start with the one that decades later finally got him the Nobel Prize.
That would be his paper on the photoelectric effect. This tackled a major unsolved problem at the time. Why certain metals shoot out electrons when light shines on them, but only if the light is above a certain frequency, no matter how bright the light is.
And the common wisdom back then was that light was a continuous wave.
It was. But Einstein proposed this radical, almost blasphemous idea that light wasn't just a wave, it was also made of discrete packets of energy, or quanta.
What we call photons today.
We call them photons today. And this explained that frequency dependence perfectly. It just solved a long-standing mystery.
And this seemingly small insight light as particles was actually the beginning of the entire quantum revolution.
Absolutely. It provided the empirical evidence needed to move physics away from the purely classical view. Even though it took years for the scientific community, people like Max Planck even, to fully accept the implications.
So revolutionary that even his Nobel Prize was careful about it.
It was. When he finally got the prize in 1921, the citation was very carefully worded to focus on the photoelectric effect, which shows you just how much scientific discomfort there still was with the idea of light quanta.
Okay, next up, he basically cemented the foundation of physical reality itself with the paper on Brownian motion.
Right. This was about the erratic, visible movement of things like pollen grains suspended in liquid. The atomic theory existed, but it didn't have conclusive, measurable proof.
And Einstein provided that proof.
He linked this visible random motion directly to the ceaseless kinetic energy of the water molecules, which were constantly battering these larger particles.
Oh, he provided the math to prove that atoms and molecules are real and that they behave predictably.
Exactly. He made the invisible, visible, and measurable. His model gave clear, testable predictions, offering concrete, undeniable empirical evidence that propped up the entire structure of chemistry and statistical physics. It finally settled the debate over the reality of atoms.
And now we get to the papers that truly redefined reality. First, special relativity. What was the core problem it was trying to solve?
SR was trying to fix a deep, fundamental conflict between classical Newtonian mechanics and James Clerk Maxwell's equations for electricity and magnetism.
How so?
Well, Maxwell's equations implied a constant speed for light. But Newtonian mechanics suggested that the speed you measure should depend on your own motion. This led physicists to invent this idea of the luminiferous ether, a supposed stationary medium that light waves traveled through.
And Einstein just dismantled that entire framework with two core principles.
He stripped it all down. First, the laws of physics are the same for all observers moving at a constant velocity. Second, the speed of light in a vacuum is invariant. It's the same constant speed for everyone, no matter how fast you're moving relative to the light source.
And when you accept that the speed of light is the cosmic speed limit, constant for all, the consequences for space and time are immense.
They're completely non-intuitive. SR showed that absolute time and absolute space are illusions. Instead, you have space-time. If you're moving relative to me, my time appears to run slower to you. That's time dilation. And my length appears to shrink in the direction of motion-length contraction.
The very fabric of reality becomes flexible.
It adjusts, so that all observers always measure the speed of light as the exact same constant. The ether, which had been the centerpiece of physics, was suddenly rendered completely unnecessary.
And this leads directly to the most famous consequence of that whole miracle year.
Yes. The paper published as an addendum derived the equivalence of mass and energy, E equals mc of A. This is the revolutionary idea that mass and energy aren't separate things. They're two sides of the same coin, related by the speed of light squared.
What does that sesapart actually signify conceptually?
It signifies the sheer magnitude of the conversion factor. Because the speed of light is so astronomically huge and then you square that number, it means a tiny, tiny amount of mass contains an immense amount of rest energy just waiting to be released.
And that's the theoretical groundwork for nuclear physics.
It fundamentally unified energy and matter. The little bit of mass that's lost when atoms fuse or split, the mass defect, that's what powers the sun, and much later the atomic bomb.
So the insights of 1905, they only applied to non-accelerating observers. But if you accelerate, or if you bring gravity into the picture, special relativity kind of falls apart.
It does.
So the next decade of his life was spent solving that much more complex problem, and it all led up to general relativity in 1915.
GR is an order of magnitude more complex than SR. It required completely revolutionary math. It wasn't just a tweak, it was a brand new theory of gravity. And the conceptual key came in 1907 with what he called his happiest thought, the equivalence principle.
I think this principle is the hardest part for most of us to grasp. Can you break it down for us?
Let's try. Imagine you're in an elevator in deep space, far from any gravity. If that elevator is suddenly yanked upward by a rocket, you feel pressed to the floor, just like you would on Earth. Now imagine you're in a closed box, falling freely toward Earth, like an astronaut in orbit. You'd feel weightless. The equivalence principle just states that, locally, you cannot tell the difference between the effects of gravity and the effects of acceleration. Freefall is inertial motion.
So if gravity is indistinguishable from acceleration, then gravity must not be a force pulling things together. It has to be something else entirely.
Precisely. Einstein realized that gravity isn't a force, it's the consequence of mass and energy, warping the very geometry of the four-dimensional thing we call space-time. The sun doesn't pull the Earth, the sun creates a curve, a valley, in space-time, and the Earth is simply following the straightest possible path through that curved space-time.
And that's where the advanced math came in. The sources mentioned Riemannian geometry. Why wasn't standard flat geometry enough?
Well, Euclidean geometry is great for drawing triangles on a flat piece of paper. But since GR models gravity as curvature, he needed a geometry that could describe curved spaces. Riemannian geometry gave him the mathematical tools he needed to describe these curved, non-Euclidean spaces, in this case space-time, and relate the amount of mass and energy to that curvature.
And the beauty of the theory was confirmed almost right away in a key test.
Yes. GR successfully explained the anomalous precession of Mercury's perihelion,
Its orb.
the slow drift in the closest point of its orbit around the Sun. Newtonian physics could never quite explain this tiny excess movement, but GR, by calculating the curvature caused by the Sun, accounted for the drift perfectly. That was a stunning early win.
That initial win was enough for the physicists, but it was an astronomical event 4 years later that launched him out of the world of science and into, well, global superstardom.
That was the total solar eclipse of May 29, 1919. Einstein's theory predicted that starlight passing close to the massive gravity of the Sun would actually be deflected or bent by a very specific measurable amount.
Much more than what classical physics predicted.
A lot more. And Sir Arthur Eddington, a British astronomer, led expeditions to measure this during the eclipse, which, temporarily blocked the Sun's blinding light, making the stars behind it visible.
And his results.
Eddington's results confirmed Einstein's calculations almost precisely.
And the public reaction was unlike anything ever seen for an abstract scientific discovery.
It was instantaneous, global, and just overwhelming. Einstein became, as you said, perhaps the world's first celebrity scientist. The Times of London ran that famous headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown."
It was a sensation.
A cultural and intellectual sensation. Suddenly, this abstract mathematician was the face of a new reality.
It's fascinating how the sheer complexity of his work actually fed into his mystique. The average person obviously didn't understand Riemannian manifolds, but they understood that this one man had redefined the entire universe.
Absolutely. His complex ideas made him seem almost superhuman, but his approachable, slightly disheveled look made him relatable. And there's that great anecdote of his meeting with Charlie Chaplin in 1931.
At the premiere of City Lights, what a moment! The world's most recognizable comedian meeting the world's most recognizable scientist.
And Chaplin famously remarked to Einstein, "They cheer me because they understand me, and they cheer you because no one understands you."
Wow.
Einstein took it in stride. Chaplin later noted that beneath Einstein's calm exterior was a highly sensitive and emotional person, the very energy that drove his incredible intellectual pursuits. He was, overnight, an ambassador for intellectual thought itself.
So, moving from that global spotlight to the deeply personal, the sources show a man whose relationships were much more tumultuous than his public image suggested. Let's start with his first wife, Mileva Maric.
Einstein met Maric when they were both students in Zurich. She was a brilliant physicist herself, the only woman in their class. They married in 1903.
And they had a daughter before they married.
Yes. Their letters confirmed the birth of their daughter, Lyserl, in 1902. But her story is a complete mystery. She either died in infancy from scarlet fever or was given up for adoption. It seems Einstein likely never even saw her. They later had 2 sons, Hans Albert and Edward.
And the marriage was under strain for years, and it ended with a very unusual divorce settlement in 1919.
It was extraordinary. Einstein agreed to give Maric the entire monetary value of the Nobel Prize he was widely expected to win. It was a huge financial commitment, ensuring her security.
Which suggests he was pretty confident he was going to win the Nobel.
Very confident. And he did, for the photoelectric effect. Just 2 years later, in 1921, the money went directly to Maric.
And soon after that divorce, she remarried.
He married his cousin, Elsa Lowenthal, in 1919. Elsa was a fiercely loyal partner who really managed his increasingly complex public life.
But that public image of the devoted scientist was complicated years later by the publication of his letters.
Yes. The release of his personal letters, especially in 2006, revealed that while he was married to Elsa, Einstein had multiple romantic involvements, including with Margaret Lebach and Ethel Michanowski. He was clearly a man who demanded both immense intellectual stimulation and, well, a lot of personal freedom.
Which made for a complicated marital life.
Very. But perhaps the deepest personal shadow was the tragedy involving his son, Edward.
Tet.
Yeah. He was brilliant, but struggled terribly with mental health in early adulthood. Around age 20, he was diagnosed with schizophrenia. This was just devastating for Einstein.
And Edward spent most of his life institutionalized.
The majority of his life, yes. Either at the Berkowski Psychiatric Hospital in Zurich or in the difficult care of his mother.
Given Einstein's relentless focus on the rational, deterministic order of the universe, this encounter with the terrifying randomness of acute mental illness in his own family must have been profoundly painful.
It was a constant source of sadness. He kept up a correspondence with his son and often wrote about his distress over Edward's condition. It's a clear and very sad juxtaposition between the father's search for cosmic order and his struggle with the chaotic reality of his own son's suffering.
So the moment Einstein's fame exploded in 1919, his platform became moral and political, not just scientific. He was a vocal anti-nationalist, a Jew, an internationalist. And as the political climate in Germany soured in the early 1930s, his position became, well, untenable.
By 1933, the Nazi rise to power was complete. Einstein was abroad. He was on a visiting professorship at Caltech in the U.S. in February 1933. He knew instantly and unequivocally that he could not go back.
And he made a very public statement about it.
He did. He said, "As long as I have any choice, I will stay only in a country where political liberty, toleration, and equality of all citizens before the law prevail."
The Nazi regime's reaction was immediate and incredibly aggressive.
They moved fast to erase him. The Gestapo raided his apartment in Berlin. His property, including his beloved sailboat, was confiscated, and he was put on a Nazi enemies list with a bounty on his head.
Wow.
He went straight to the German consulate in Antwerp and formally renounced his German citizenship for the second and final time.
And they didn't just target him physically, they went after his ideas, which led to the infamous book burnings.
Yes, his works were among those burned. He understood this wasn't just vandalism, it was a profound ideological act. He condemns the book burnings as a spontaneous emotional outburst by people who shun popular enlightenment and who fundamentally fear the influence of men of intellectual independence.
To the Nazis, his physics was Jewish physics.
A threat to their racially defined pseudoscientific worldview. But he turned his unique global status into a tool to actively fight the persecution of others.
He became a huge advocate for displaced scientists.
An extraordinary advocate, he worked with organizations, contacted world leaders. He reached out directly to Winston Churchill to secure British help for scientists fleeing Germany. And even more remarkably, he wrote directly to Turkey's Prime Minister, Ahmet Ince, in September 1933.
Why Turkey specifically?
Turkey was going through this period of intense modernization and secularization under Ataturk. Einstein leveraged this, arguing that these persecuted academics could contribute immensely to the new Turkish universities. The sources indicate this advocacy resulted in over 1,000 saved individuals.
1,000 people. That's a stunning, tangible legacy of his political engagement.
It really is.
His dedication to human rights and his opposition to violence, it highlights one of the most profound paradoxes of his life. The lifelong, devoted pacifist who became the key stimulus for the development of the atomic bomb.
He called war a disease. He was a fervent advocate for world government. His pacifism was deeply, deeply held. But 1939 forced a terrible moral compromise.
This is where Leo Szilard comes into the picture.
Szilard and other Hungarian scientists had definitive proof that nuclear fission was possible, and they feared that Nazi Germany was actively trying to develop a weapon based on that technology.
And Szilard knew he needed a voice that could not be ignored.
So he sought out the most famous scientist in the world, the reluctant pacifist Einstein. And Einstein, despite his deep reservations, was convinced of the urgency.
He was convinced that the immediate existential danger from Hitler's Germany outweighed his pacifist ideals.
He was. He signed the famous 1939 letter to President Franklin D. Roosevelt, urging the U.S. to start its own research into extremely powerful bombs. And that letter is considered the key stimulus for the U.S. government launching the Manhattan Project.
The weight of that decision must have been immense, especially after the bombs were actually used in 1945.
It was an overwhelming burden. While he never worked directly on the Manhattan Project, his signature started it. Later in life, he voices immense regret over and over. He told his friend Linus Pauling that signing the letter was his one great mistake in my life, though he always maintained he felt justified at the time, given the danger.
And he spent the rest of his life working for nuclear disarmament.
Vehemently.
After he adopted U.S. citizenship in 1940 and settled in Princeton, his activism then shifted to the domestic struggle for civil rights.
Yes, his involvement with the NAACP was immediate and passionate. He spoke out forcefully, comparing the plight of African Americans to his own experience fleeing discrimination. He did not mince words. He called racism America's worst disease.
A sickness handed down from one generation to the next.
Exactly. And this wasn't just abstract political theory for him. This was a personal commitment, which you can see in that famous story about Marian Anderson.
The great Simmer.
The acclaimed black contralto. She arrived in Princeton for a concert in 1937 and was refused a room at the local upscale Nassau Inn because of her race.
And Einstein heard about this.
He heard about it and immediately invited her to stay at his home on Mercer Street.
That's a powerful public act of defiance in the segregated 1930s.
It was, and it wasn't a one-time thing. He extended that invitation, hosting her whenever she visited Princeton for concerts, right up until he died. He showed that moral responsibility required active engagement, making his home a sanctuary against injustice.
This takes us to the final and most intellectually agonizing phase of his career, at the Institute for Advanced Study in Princeton. After reaching the summit of classical physics with general relativity, the man who helped launch quantum theory spent his last decades fighting the probabilistic chaos that the quantum world seemed to embrace.
It's the second great scientific irony of his life. Quantum mechanics, which governs the subatomic world, introduced fundamental uncertainty and probability into nature. For Einstein, the universe had to be orderly, deterministic, and complete. He famously declared his opposition by saying, "God does not play dice."
He just could not accept that the underlying reality was inherently random.
His whole intellectual foundation, rooted in Kant and that search for deep, elegant coherence, it just rejected randomness as a fundamental property. He believed the apparent randomness was just because we had an incomplete description of reality. There had to be hidden variables that, if we knew them, would restore the deterministic order.
And his most sophisticated challenge to quantum theory came in 1935 with the thought experiment known as the EPR paradox.
Correct. Working with his colleagues Podolsky and Rosen, he tried to prove that quantum mechanics was incomplete. The paradox is based on quantum entanglement, the idea that two particles, once linked, remain instantaneously correlated no matter how far apart they are.
And how did entanglement challenge relativity?
Well, if you measure a property, like spin, on particle A, you instantaneously know the corresponding property of the distant particle B. Einstein argued that since special relativity forbids any influence from traveling faster than light, a principle called locality, this instantaneous correlation must mean the properties of particle B already existed before the measurement.
So the quantum theory, which says the properties only become real when measured, must be incomplete.
That was his argument. He saw this instantaneous, spooky action at a distance as a fundamental breakdown of physical reality itself. If one event here instantly affects something kilometers away, it violates his core principles.
And that leads him directly to his intense and ultimately isolating quest for the unified field theory.
He sought an even grander mathematical theory. His goal was to merge gravity, which GR described beautifully with electromagnetism, into a single, cohesive geometrical field theory, one set of equations that described all fundamental forces.
Why did this quest end up isolating him from his peers?
While Einstein was pursuing this one singular goal, using complex classical geometry to unify forces, the rest of mainstream physics was moving in the complete opposite direction. They were embracing quantum mechanics, developing quantum electrodynamics, exploring the nuclear forces. His quest for a purely classical deterministic unification, without the probabilistic framework that was defining the new age, led him to become increasingly isolated.
A tragic, heroic dedication to a principle.
The principle of deterministic harmony that science, at least for the time being, had moved past.
So we conclude this deep dive into the man whose name is, well, it's shorthand for genius. We see a scientific revolutionary whose achievements were matched only by his contradictions. The man who created modern physics in a patent office, the lifelong pacifist who triggered the atomic age, and the father of quantum theory who fiercely rejected his own creation.
His legacy is defined by that fierce independence and intellectual elegance, whether he's challenging gravity or challenging social norms. And to bring us back to the personal source of his emotional strength, we have to remember the profound role music played in his life.
It was more than just a hobby for him. It was an emotional necessity.
It truly was. He was an avid and skilled violinist, played almost every day. He found profound solace and reflection in music, especially the compositions of Mozart and Bach.
He preferred Bach to Beethoven.
Yes, he preferred Bach's rigorous structure and clarity over, say, the emotional intensity of Beethoven. And he had a beautiful insight on how he learned.
What was that?
He refused to practice systematically. He said he only truly embraced the violin after discovering Mozart's sonatas around age 13. And he summed up his philosophy of learning and passion perfectly, saying, "Love is a better teacher than a sense of duty." He was seeking the underlying harmony in music, just as he sought it in the universe.
In that search for elegance, for harmony, it manifested right up to his final moments.
It did. In 1955, when he suffered a fatal abdominal aortic aneurysm rupture, the sources say he refused surgery to prolong his life artificially. He saw it as a violation of the natural order.
He made a famous statement about it.
He did. He said, "I want to go when I want. It is tasteless to prolong life artificially. I have done my share. It is time to go. I will do it elegantly."
A profound refusal to impose artificiality onto a natural process.
Exactly. And given his lifelong philosophical belief that a spirit is manifest in the laws of the universe, this final act of refusal, choosing natural elegance over artificial prolongation, it raises a final provocative thought for you. Did this final choice reflect his ultimate acceptance of the beautiful, deterministic natural laws he dedicated his life to defining? Or was it just the final, uncompromising act of intellectual and personal independence? That's the question that echoes long after the physics is understood.